having integer multiples.
All right, I think we are going to get started. Or should we wait more? It's 3:45. Get started? Okay. So the place where we left off in the morning was the discussion of how to build the so-called Chiral Lagrangian. Yes, so we found the variable, the nonlinear sigma model field. Yes, so that field was this u equals e to the 2I pi ta over f. Yes, and we found how this pion field is supposed to be the Goldstone boson. Yes, and we found how that pion transforms under the unbroken and under the broken generators. Yes, so under the unbroken symmetries, it transforms just like as a normal linear transformation, as everybody is used to normal rotations. But under the broken symmetries, there is a shift symmetry. Yes, so that's the unusual part. That is the one that is telling you that there is a nonlinear realization going on of the global symmetry. Yes, and that's the part that I mentioned is giving you sort of another proof of Goldstone's theorem, because under the broken symmetries, the pi is just going to pick up a shift by a constant. Yes, so this, for example, forbids any non-derivative interaction term. So that tells you that the Goldstone cannot have, in the limit when there is no explicit breaking, cannot have any non-derivative terms. Very good. So how should we then actually write down an effective Lagrangian for the theory? Yes. So well, we are just going to use this u of x field, yes, and write down all the terms that are actually consistent with the symmetries. All terms consistent with the full symmetries. Some are linearly realized, some are non-linearly realized, but this still will be will be reflected on the Lagrangian. Yes, and the other thing that we do is we will sort of organize them by the number of derivatives. So what this is going to give you is basically an expansion in the, it's a low energy effective Lagrangian, and it's an expansion in momentum over f squared. Yes. All right. So what's the first term that is invariant under all the symmetries? Yes.
Excuse me.
Yes.
If you have explicit breaking, would your power matrix keep changing?
Right. So when there is explicit breaking, we will discuss how to do that. Yes. So we will do Spurion analysis then. Yes. We will have to find out what the source of the explicit breaking is. Yes. And then try to write down terms. Well, we'll get to that in a moment. Very good. So first is terms with no derivatives. Yes. How many terms can we write? Well, we can write superficially some terms, but already this argument about the shift symmetry told us that there better be none. Yes. So the only invariant that you can write, yes, is u dagger u. Yes. So just to remind you, yes, how does the u transform? U of x transforms as u left, u right dagger. Yes. So you can make an invariant without derivatives. Yes. But this is proportional, or a trace of this. Yes. But this is proportional to the unit matrix. Yes. Because this u is e to the I pi a ta over f. Yes. T is a generator. It's Hermitian. So this is a term that doesn't contain the pions, which is, of course, is not a shock. Yes, we knew from the shift symmetry that there better be no terms without derivatives. Yes, so that's consistent. Yes, and then you can write terms with two derivatives. So this is the one that is usually just used. Yes, so two derivatives. So well, you can take d mu u dagger d mu u, yes, and then take the trace of that. Okay. And then there is an arbitrary coefficient in front of this. Yes. I'm going to call this arbitrary coefficient f squared over 4. Yes. Why do I call it f squared over 4? Because this is also the piece that is supposed to give you the kinetic terms of the pions. Yeah, so if I now plug in u, I can get this as an expansion in terms of the number of pion terms. Yeah, so there will be a piece here. So you just literally plug in here e to the I 2 pi a ta over f. Yes, take the derivative. Yeah, that will bring down the pion field, take the traces, etc. And you will start expanding it, and then this coefficient is fixed such that you get the canonically normalized kinetic term for the pions. Yes, so you get the term d mu pi a squared. Yes, so that's good. Oh, I'm violating U-dice rule. Yes. It's fine, but then over there maybe.
The first one is fine. The last one is.
Oh, it's the back. Yeah, that's further back. Okay. Anyways, and then you will get other terms. Yeah, so you will get terms that are of the form d mu pi squared times pi squared. Yes, and then this will have a 1 over f squared term. Yes, and terms with more pions. Yes. So this term will basically tell you what the leading expression for the pi scattering is. Yes. So this will tell you the pi goes to pi scattering. Yes. And of course, you could go on and add additional, higher terms with more derivatives. Yes. Those will truly have now unknown coefficients. Yes. This one didn't quite have an unknown coefficient, though of course we haven't quite fixed what f is. Yes, but we'll get to that in a moment also. And okay, so you can get additional terms. Then you will of course have to fix them, from some experiment, and you can go ahead and do this. So this is what is called chiral perturbation theory and the chiral Lagrangian. Very good. So that's just QCD. Now, how about the electroweak symmetry? So the electroweak symmetry. Well, we already said that the electroweak symmetry is contained as a subgroup. SU2 left cross U1 is a subgroup of these global symmetries of SU3 left cross SU3 right cross U1b. Yes. So all you do is, then in order to introduce this gauge symmetry, you know how to gauge a global symmetry. Yes. You know how these nonlinear sigma model fields transform under the global symmetry, and you know how to gauge a global symmetry. Yes. You just promote your ordinary derivatives to covariant derivatives. Yes. So you will have the d mu of u of x. Yes. Let's say it has two indices, the left and the right. Yes. There will be a piece that is, so it will have the ordinary derivative as usual, u of ij, and then there will be a piece where SU2 left is part of the SU3 left subgroup. Yes. So there will be the usual W gauge bosons will be acting on this first index here, which is the SU3 index. Yes, so minus Ig W mu A times 1/2 tau Ik, and this is acting on the SU3 index. Yes, and then you are embedding here the hypercharge is a subgroup of SU3. Yes, so hypercharge is going to be a subgroup of T3, right? Okay, so you will get another piece here, G prime B mu times 1/2 T3 right, Kj, and now this is acting on the SU3 index, U I K. Okay, so that's the rule. That's a simple rule of how to include the electroweak interactions here. Yes. Now, one important thing is that while SU2 left is embedded as a subgroup of SU3 left, and QCD is breaking SU3 left. Yes. So this means that QCD is already breaking the electroweak symmetry. So the fact that you have the quark condensates is already giving you a source for breaking the electroweak symmetry. Okay, so as right, yes. Well, so this is not strange. Yes, this is the pion matrix. Yes. So, right, is broken to the diagonal subgroup. Yes. So this is already giving you an explicit. Well, is already giving you a breaking, not an explicit, but a spontaneous breaking of SU2 left gauge symmetry. Yes. So QCD, the fact that you have the quark condensates is already contributing to the electroweak symmetry breaking. Yes. And you can see this from the chiral Lagrangian. Yes, because when you are expanding your nonlinear sigma model field, yes, it contains a piece that is proportional to 1, yes, piece without pions, yes. And so that means that the covariant derivative of U, yes, will give you a piece. Oops. Yes, will give you a piece that is IGW mu A tau A over 2 plus IG prime B mu 1/2 tau 3. Yes, very familiar term. Yes, this is exactly the kind of term that you have when the Higgs is getting an expectation value. So when you plug this in, yes, the F squared over 4 d mu U dagger d mu U, the trace of that, yes, is going to contain a mass for the W and the B. Yes, so it will contain a mass G squared F squared over 4 W mu plus W mu minus, yes, plus the usual thing G squared plus G prime squared over 4 F squared. Larger, okay. Upshot is QCD breaks the electroweak symmetry and gives you an expression for the W and the Z, a contribution to the W and the Z mass, just like the one that you are used to from the usual Higgs mechanism. Yes, so this is just like the Higgs, except, yes, V is replaced by F. Yes, except V is replaced by F. Okay, where F is what we call the pion decay constant. So how large is F? Well, we can get that explicitly also from experiments, yes, because when you write down this chiral Lagrangian, yes, there is a mixing term between the W and the pion, yes, and this one everybody can see here or not? From the chiral Lagrangian, yes, there is a contribution there that is a mixing between the pion and the W, yes, F times W mu plus D mu pi minus, yes, plus Hermitian conjugate. So this is also a very familiar kind of term, yes. This is telling you that if QCD was the only source for electroweak symmetry breaking, yes, then the pions, so these pions are the true pions of QCD, yes, would actually be eaten by the W. Yes, of course, what happens in reality is that you have the true pions, plus you have the Higgs. Yes, both of them are contributing to electroweak symmetry breaking. and the Higgs contributes a lot more. So a small combination of the true pions is part of the Eton guy, and it's mainly the terms from the electroweak doublet that are actually the Eton guys. But if there was no Higgs mechanism, yes, the W and the Z would already be massive. Yes, the pion would truly be an Eton field. Yes, but if you take this seriously, yes, then you can actually find what the decay of the pion is going to be. Yes, so this is why this is called the pion decay constant. Yes, so you can think of this as here you have a pi plus. Yes, there's a mixing here that is proportional to the momentum. Yes, here you have W plus, and then here you decay to a muon and a neutrino, whatever, mu plus mu. Yes. And so here from this vertex you will get G times F, and then here from the propagator, this is a low energy guy, so it's roughly just mW squared. Yes, there is a momentum here that will give you a pion momentum. Yes, so from this you can go ahead and calculate what actually the decay rate of the pion is. Yes, so this is why this F is called the pion decay constant. Yes, and again you can just read off from measuring this rate. Yes, and you will get that something of the order of 130 MeV. Okay, very good. So it's below a GeV, so you will get a mass less than a GeV contribution from QCD to electroweak symmetry breaking. So this is a very, very important conceptually. Of course, numerically it turns out to be not so important, because the mass that you get to the W and the Z happens to be just too small, but it's actually there. Yes, so it is a true contribution to the mass of the W and the Z. Very good. And so if you were to calculate the W propagator, so the W is going to interact with the strong dynamics, yes, whatever is giving rise to this chiral Lagrangian. Yes, so you will have the normal contribution here, plus you will have here the blob from the pions. Yes, and you can add many of them. And of course, to leading order, this blob is just, this mixing. Yes, so to leading order, you will just add this term. How will that term look like? What does this term do when I'm going to sum up the yes?
Is lab sensitive enough to actually get at this contribution to the W mass?
Oh yes,
of course. That's already been noticed.
But but there's something really important. Yes. So this would be so 100 MeV. Yeah, it's you know the W mass to better than that. Yes, but the important thing is that it's just another contribution. It's sort of indistinguishable from what is coming from the Higgs and what is coming from QCD. And the reason why it's indistinguishable is because it gives you the same ratio, the same mass ratio as what the Higgs does, which at this point looks like a miracle. Yes. So it's not only that it gives you a contribution to the W and the Z, but you get the same W over Z mass ratio. Yes? So it's really, indistinguishable of what you call V from the Higgs, yes, or V squared goes to V squared plus F squared. Yes, it's really just purely a rescaling. Yes, so it doesn't have a, you cannot experimentally separate, which one is the QCD contribution and which one is the contribution from the Higgs, yes? And that's because it has the same structure, okay? And then why does it have the same structure? Yes, well, we'll talk about that. It's not a coincidence, of course. That has a symmetry reason. Yeah? So that's called the custodial symmetry. Okay, so that's a good question. So, all right, so what I wanted to say also is that just another way to see, of course, that the W is going to pick up a mass is just go ahead and calculate the W propagator, because you have this mixing with the pion. Yes, here you will have a P and the P showing up, and then an F, and then an F, and then here you have a massless pion, 1 over P squared. Yes, and then you sum this up. As usual, this is something that goes into the denominator. Yes, so basically the propagator, you had the usual Q squared propagator for the MW without this effect. Yes, and then here you will pick up the additional contribution G squared pi squared of Q squared. Yes, where this pi squared, sorry, the pi of Q squared. Yes, where this pi is just going to be this blob, which at 3 level is truly just going to be f squared times some constants, which I didn't write down here. Yes, it's going to be I over Q squared minus G squared f squared over 4, and then there's the usual G mu. Okay, so it truly shifts the location of the pole of the W. Yes, so it is really going to give you, as usual, the contribution to the mass of the W. All right, so that's the story of electroweak symmetry breaking from QCD. Now, on to what happens to explicit breaking terms. So there are several sources of explicit breaking. Yes. Yes. I'm sorry? Yes, so that's also an explicit break. Yes. So that's also an explicit breaking. Yes. Okay, let me say it. Other sources of explicit breaking. Yes. And what is their effect on the chiral Lagrangian? Yes. So the most important one is the fact that the quark masses are non-zero. Yes. So we are talking about a theory with 3 quarks. Yes. So there is a mass term. Yes, which is going to be m up, m down, and m strange. Yes. And then the way you would write it in QCD, yes, so you will write it as a Q bar Q. Yes. So the way you should be dealing with these explicit breaking terms is to ask the question, well, so this one doesn't actually have the same symmetry as the chiral Lagrangian that we were starting out with, yes. So it doesn't have the SU3 left cross SU3 right symmetry. So the question is, what effect is it going to cause in the chiral Lagrangian? Yes, go ahead.
So in this case, then pi pick up the mass from the disk breaking term?
I'm sorry?
We just calculate the W mass term from the disk mixing, but the backwards, pi can pick the mass as well from the disk mixing.
Well, so if pi was the only thing that was there, yes, and there was no Higgs, whatever, yes, pi would just be the longitudinal component of the W. So there's a Higgs mechanism, and then so this is an explicit breaking, yes. So for example, there is the usual electromagnetic contribution, yes. So I would think there's probably a contribution from the W as well, yes.
But I guess it's subdominant to what you're.
Yeah, I think so. So it doesn't have the SU3 left cross SU3 right symmetry. Yeah? So then the question is, how should I include the effect of this explicit breaking on the chiral Lagrangian? Yeah? So for this, there is a really important trick, yes, which is called the Spurian analysis. It is saying that, well, yes, this term is really truly not invariant under the symmetry. Yes, SU3 left cross SU3 right, because there is this explicit matrix here that's made out of numbers. Yes. So what you can do is you can say, well, let me sort of imagine another theory. Yes, where this wasn't just a bunch of numbers, yes, but this was actually a field. Yes. So I'm going to call this capital M, and I will imagine for a moment that this M, which actually is truly just a bunch of numbers, is a field. Okay. So then the question is, how should this field transform in order for that term that I wrote down that at this moment is explicitly breaking the symmetry would actually be invariant under the symmetry? Yes. So I want to ask, so let's pretend that this M, yes, so one of these is a left-handed quark and the other one is a right-handed quark. Yes. And so these fields transform as a bifundamental, yes, it transforms as a 3 bar under SU. So the Q bar Q, yes, transforms as a 3 bar under SU3 left cross SU3 right. Yes. I mean, each of them is a fundamental. Yes, whether it's fundamental or anti, that's a matter of convention. Yes. But what I'm saying is that let's pretend that M was a field, yes, that transformed in the opposite way. Yes. So if M transformed in the 3 bar 3 of SU3 left cross SU3 right, yes, then this term actually would be invariant. Yes. And then, of course, what I'm going to say is, let me imagine that this was a field that for some reason got an expectation value. Yes. Its expectation value happened to be, well, whatever those quark masses are. Yes. And then ask the question, how is this field supposed to show up in my effective chiral Lagrangian? Yes. Up in this chiral Lagrangian. Well, again, if this was just a true, interacting field that is light, whatever, yes, well, it better show up such that the full Lagrangian is invariant under SU3 left cross SU3 right. Yes. How can I make a term like that? Well, I can make a term that is just, M times U. Trace of M times U, yes, plus Hermitian conjugate to make sure that the whole Lagrangian is real. Yes. That's how it would show up, yes, if this was a field. Because, this transforms as 3 bar, this transforms as 3 bar 3, yes. So if I take, if I multiply them and take their trace, that's an invariant term. Okay. And then I say, well, okay, so now let me say that I had this theory with the field. Now let me freeze the field to its expectation value, yes. You still expect that this is the way it is going to show up in my effective low energy Lagrangian eventually. Okay, so of course, eventually when you do this Purian analysis, you don't go through all of these steps, pretend it's a field. You just say, well, look, there's an explicit breaking. I'm going to call this a Spurion. I identify how this Spurion transforms under the symmetries, yes, and then I just use that to write down what the effective Lagrangian in this theory would be.
Isn't another way to guess this just to say take the limit that all the quarks have the same mass, so reducing it into an infinity. Then you get a SU3 vector symmetry that respects that. I think that set identity should respect SU3D, which is the same as trace of U, which is you can see right there reduces the.
It's basically the same argument, yes. Right. Again, I just like to make sure that you understand that this method is something very general, yes, and it's used in many parts of particle physics, yes. Many of the so this is how explicit breaking terms are always taken into account, yes. So for example, when you're talking about anomalies, you can sort of pretend that the dynamical scale of the theory is actually transforming under the anomalous symmetry, and with that you can write down what the form of instanton generated terms is. So this is really a very general method. So I wanted to make sure that you understand this. It's not specific to the chiral Lagrangian, of course, but I guess this was the first place where it was used. Okay, and then now this is nice because now you have an explicit form of this explicit breaking term. Yes, so you can go ahead and expand. Yes, now your nonlinear sigma model filled in terms of the pions. Yes, so you will get here a term that is m times pi a t a over f squared. Yes, you have to take that, the trace of that, plus, I guess the Hermitian conjugate piece cancels out the linear term. Yes, so there is probably just an overall coefficient, and so what you find is that you will get contributions to the pion masses. Yes, so the pion masses, so delta m. So these are true mass squares as they have to be for the bosons. Yes, and those will be proportional to quark masses divided by f squared. Yes, so the contribution to the mass square of the pion will be proportional, linearly proportional to the quark masses. Yes, divided by f squared, and there is of course some other constant that is making up the right dimensions. Okay, so from this you can derive famous formulae like the Gell-Mann-Okubo mass formula, because you just expand this. Yes, you put in m up, m down, m strange. Yes, you put in 3 quark masses. Yes, and then there are four of these different pions, so there will be one mass formula there. Yes, one relation. Yes, that's called the Gell-Mann-Okubo formula. M eta squared plus m pi squared equals 4mk squared. Okay, so you get a relation like this. That's assuming that the up and the down mass is roughly equal. Okay, so this is how you are doing explicit breaking. Very good. Yes?
Masses were equal. I expected something of an symmetry that made this effect go down.
Sorry, well, then so you didn't break it explicitly down to SU. Well, so there would be additional, there would be similar kind of, explicit breakings from Electroweak. So, for example, you can write down a similar story. I have it here in the notes. You can look it up for charge, for electric charge. Yes. So yes, but this is the most important one, and we have to. Yes.
Related question. So, in this alternative theory, at high energy, we're having fields MQ and Q bar, right?
Right.
And at low energy, we spend the tidal field
instead of the quarks. But M is exactly so. The idea is that M is not interacting strongly. Yes, it has its own dynamics, but doesn't interact strongly. Yes. So as you go to the low energy theory, the Qs, they form whatever they do. Yes, they form pions, they break the chiral symmetry, blah blah blah. But M just, M is just remaining there. Yes, because it has its own thing, and its only role, yes, is to give you these masses. Okay. That's sort of an even more complete version of the Spurian analysis story. All right, very good. NDA. So we have a sort of a nice story about how to write this effective chiral Lagrangian. Sorry?
What's the sense of scale of mu? Is it lambda QCD?
So the way you do this, yes, is that you calculate what the masses of the pions are, yes. So they will be proportional to mu and the quark masses and F, yes. So this is an unknown parameter for us, yes. And it's going to, well, again, so let's see, yes. parametrically, yes. So the pion mass squared, yes, will get a contribution of the order of mu cubed, yes, times the quark mass, yes, divided by f squared. Okay, so now you know this is 100 MeV, yes. This is also 100 MeV squared. Well, this is a small quark mass, yes. That's how you roughly fix it. What is the value of mu? Okay, mu cubed equals f squared m pi squared, yes, over m cubed.
From the low energy,
Yes.
experiment, is there any like argument for related to other?
You mean how to calculate this from first principles? I don't know. I think that's like, solving QCD with, all of this.
Well, I mean, some other cases, it's just not like this.
It's right that with the dimensions then
All right. NDA and the cutoff scale. So this Chiral Lagrangian, yes, the one that we have written down here, yes, is clearly a non-renormalizable theory, and nobody even claimed that it should be. There's no reason why it should be a renormalizable theory. It's a low energy effective theory. That's how we started out. Yes, we said that, well, we have this, this potential, and we are going to get rid of all the heavy degrees of freedom, and just try to write down a Lagrangian for the Goldstone bosons. Yes, but then the question is, where does this theory break down? So where is the cutoff? Yes, and that's going to be important, yes, because we will be using, these kind of Lagrangians to build the these composite Higgs or pseudo Goldstone composite Higgs model. So we want to understand where does it break down. Yes. So let's take the simplest example. Yes, and I mentioned to you that there is a term in the Lagrangian when you expand the kinetic term, the d mu u absolute value squared, the trace of this. Yes, there is a pion scattering term. Yes, and it will have the form pi squared times d pi squared 1 over f squared, yes, times some order 1 coefficient. Okay, so how should I find what the cutoff of this theory is? Yes, well, what I'm supposed to do is I'm supposed to try to calculate the corrections using this non-renormalizable vertex, yes, and try to find, yes, how high can I take the energy scales such that the correction does not become larger than the original term in the theory. Yeah, so this is what is called naive dimension analysis. So NDA. Let's calculate the corrections. Calculate the loop correction. Yes. For example, from this term to itself, yes, and demand that the correction is less than the 3-level term. Yes. So this is basically saying this is once this term gets bigger than the original term, the theory will definitely not be sensible. Yeah? So this is basically the highest the cutoff scale could possibly be. So at that scale, something new has to happen for sure. So there is probably some new particles or some new interactions. Yes, it could be that those particles come in earlier. Yes, but you can definitely not push the cutoff scale to be higher than that. Yes, so let's try to do this explicitly here. Yes, so let's calculate the correction to this. Yes, so how will that correction look like? Yes, well, we have two of these vertices in there. Yes, so there will be, each of these vertex has a 1 over f squared. Yes. Now each of this vertex also has two derivatives. Yes, there's one loop. Integral d 4. Yes, but usually once you do a loop integral, one loop just gives you a 1 over 16 pi squared eventually. So I will always, when I have a loop, I will just write the 1 over 16 pi squared factor. Okay. I have two propagators here. So I have 1 over k squared squared. Plus I have two derivative interaction vertices. Yes. So you would think you should write a k squared squared, but of course I'm trying to see how large a correction this gives to my original derivative interaction. Yes. So two of those momenta have to be external. Yes, and two have to be loop momenta. Yes, so I will write here as a k squared. Yes, and then there's a p squared, which is just going to give you the derivative that you're trying to reproduce in your original Lagrangian. Okay, very good. So that means if I add up all of these terms, it's 1 over 16 pi squared, f to the 4. Yes, then there's a p squared, which is just that derivative term. Yes, and then there's an integral d4k over k squared. Yes, so this is quadratically divergent. Yes.
Could you explain again why it's p squared exactly? I mean, it depends on whether it is acting on the inside, the property of the inside, or the outside.
What I'm trying to say is that, of course, you will have here p1, p2, blah blah blah. Yes, but two of the momenta will have to end up to be external momenta. Yes, because I'm trying to calculate a correction to this vertex. Yes, which has two derivatives in it. So two of those will have to end up to be external momenta. Yes, and the rest has to be loop momentum. At least the most divergent part of it. Okay. Okay, is this clear? So this piece here is quadratically divergent. Yes. So here I have it. Yes. So I have the correction. I didn't use this yet. Yes, so what I find is that this loop correction here, yes, will have the form of the original interaction vertex, yes, times this factor here, lambda squared over 16 pi squared f squared. Yes. And so the claim is that this factor better be less than 1. Yes. Once it's bigger than 1, I definitely am outside the regime of the effective theory. So lambda is roughly equal to 4 pi f. Or maybe it's better to say it's less equal than 4 pi f. Yes. So this is basically the largest scale where new particles must appear. So this lambda is the latest scale where new particles appear. I'm sorry?
No, I'm joking.
Yes, so that's a homework for you, Dai. Get the symmetry factor.
There are also two more diagrams.
There are more diagrams. Yes, that's your homework.
Is it a coincidence that 4 pi f is roughly lambda p? I mean, we could have measured, like, say we don't know what f is, and we measured
Well,
it turned out to be 1 eV. So
No, that's what I'm saying, that it shouldn't be a coincidence, yes? You do expect lambda to be at 4 pi f if the theory is a truly strongly interacting theory. Yes?
No, but I'm saying the definition of lambda, you can get it from RG or something. And then you write the Chiral Lagrangian, and you do experimental bias, and we could have gotten, measured f that is way smaller than that. And then the theory that we write 4 pi would only be valid for 4 pi. And then there would be a gap between that and lambda.
Well, so what could have happened is that there are some particles that are lighter than 1 GeV, yes. But
I can rephrase the question. I think the question is, why is the proton roughly 4 pi times the pion decay constant?
right, so that's what you generically expect in a theory, yes, that is truly strongly interacting, yes, where the interaction strength among the hadrons is large. Yes, that's the relation you expect between the chiral symmetry breaking scale and the cutoff scale. Yeah, so that's the scale. So this is the scale, yes, where new particles have to show up. Now, whether it's 4 pi or 2 pi, yes, that's that's a little bit of a question. Yes, new particles have to show up. So no, I don't think it's a coincidence. Yes, that's what you expect. Yes. Now, of course, it could be. So that's where they have to show up if the interaction strength, yes, let me call that G star, yes, is something of the order of 4 pi. If this is a truly strongly interacting theory, yes, that's where you expect, the heavy particles to show up. But this is, for example, not true for the Higgs, yes. I mean, you could have written a similar chiral Lagrangian for minus mu squared h squared plus lambda h to the 4, yes, and then just say, well, I have a theory of the Goldstone bosons, and I integrated out the radial excitation, yes, and of course the radial excitation is not strongly interacting, yes? So there, you will have a new particle coming in earlier, yes, and what sets how early that new particle is coming in? Well, it's the interaction strength of that particle, yes. So if the interaction strength is 4 pi, yes, so it's a truly strongly interacting theory, then you do expect, the mass of your new particles, where the cutoff is, to be at 4 pi f. In other cases, yes, generically, yes, what you expect is that there will be new particles showing up at what scale? Well, whatever that interaction strength is, yes. Generically, you expect new particles to show up at G star f, yes, where the G star is, again, for the case of the Higgs, yes, well, it's actually root lambda, yes, because that's what is setting the mass of those particles. But that's roughly where the new particles will be. So this is the kind of estimate that we will be using in these composite Higgs models, yes. And so if G star is less than 4 pi, yes, then it means that there will be quadratic divergence that is cut off before you actually reach the full cutoff scale. Yes, and that will be very important because these so-called spin 1 and top partners will always be of this form. Yes, so whenever you have your little Higgs theory or whatever composite Higgs, you will need some of these particles to actually show up, yes, and get rid of the divergences, yes, before you actually reach the cutoff scale of the theory. Right. 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 Yes. But again, it doesn't completely have to be exactly like that always. And in fact, in the theories that we will be interested, yes, we will have other particles, yes, and those are the ones that we will call the gauge partners and the top partners, which will come in before you reach the full interaction strength of the theory. And again, so that's going to play an important role. Okay, so just to be completely explicit and complete, then how do you actually do NDA for a generic theory of Goldstone bosons? Oh, I should be raising these, yes, after I... It's too late if I raise it when it's useless. Yes. I'm sorry?
What if we use DIMRAG?
Well, again, you are not supposed to be using DIMRAG because this is supposed to be telling you that there is something happening at that scale. There will be new particles coming in, yes? This is just like I was arguing about the hierarchy problem, yes? This is supposed to be, representing the fact that there are physical new particles showing up at that scale where your cutoff is. Okay. All right. So how do you do then? How do you write down the estimates for a Lagrangian? Yes. So every Goldstone field should come with a 1 over f. Yes, because, well, the Goldstone is always coming from this nonlinear sigma model field e to the pi over f, yes? So there's, every time you have a field, you have to write a 1 over f. And so this is an expansion from e to the I pi eta over f. Yes. All the remaining dimension full quantities will be made up by m rho, okay, which is g star f. And so, for example, when you have derivatives, yes, you write it as d over m rho, yes, if you want to have dimensionless expressions, yes. And then there's one thing that you have to make sure that you get a canonical kinetic term, yes. So your Lagrangian will look like something like m rho to the 4th times a function of fields over f and derivatives over m rho. Yes. And you have to make sure that you get a canonically normalized kinetic term. So if you write out how a kinetic term would look like using these rules, yes, that would be m rho to the 4 times field squared, yes, phi squared over f squared, derivative squared over m rho squared, which is g star squared f squared, and then this is g star to the 4 f to the 4 divided by g star squared f squared d phi squared. Yes. So this is actually a g star squared times d phi squared. So the whole Lagrangian eventually has to be divided by g star squared, yes, in order to get the canonical, the normalized kinetic term.
But phi is pi?
Phi is pi, yeah. Yeah, sorry. I don't know why I changed here. Okay, so this is the rule for how to estimate eventually the sizes, using this NDA stuff for the different terms. So, for example, if you're asking how large a quartic Higgs pion self interaction will look like, using these rules, you will get that it's g star squared times pi to the 4. Okay. All right. So these are the rules of the chiral Lagrangians and writing down effective Lagrangians for strongly interacting theories. And now we are finally getting to the point of trying to actually use this for electroweak symmetry breaking. Okay, so how should we try to do that? Well, again, the simplest idea would be the one that I mentioned in the first lecture in the morning, which is to just say that, well, QCD breaks the electroweak symmetry. It gives a mass to the W and the Z. But that mass that you're getting is just too small. It's less than a GeV. So let's just scale up QCD, add another strongly interacting sector, and basically just repeat QCD once more. Okay, so the simplest idea repeat QCD at a higher scale. Yes. So you have another strongly interacting theory. It has its own SU2 left cross SU2 right global symmetry. Could be SU3 left. It depends on what exactly the details of that strongly interacting sector is. Yes, that's of course now a matter of the choice for the model. Yes, it has to have at least this. Yes, because of course you need the SU2 left in order to embed the gauge symmetry, and then we'll discuss later in order to have this custodial symmetry that I mentioned, this right pattern of W and Z mass, you need this SU2 left cross SU2 right symmetry, and that's broken to the diagonal subgroup. Okay, just by a quark condensate. So this is called, let me call this a capital Q and the capital Q bar. Yeah, so it's just an analog of QCD, and the quark condensate is going to break the symmetry. Yeah, so this model is called Technicolor. Okay, and it's truly a simple model. Yes, you can take all the previous formulae and just rescale, lambda QCD to lambda Technicolor. It's it's a very simple model, but it will give a mass to the W and the Z. It has a much harder time to give a mass to the fermions, though there's another way how to do this, and besides the way people were trying to use it in the 80s, that's the one that we will be discussing for composite Higgs. But anyway, it's simple. It gives a mass to W and the Z, harder time for fermion masses. But it has two other very big problems. One is, well, it's the obvious one, yes, it doesn't give you a Higgs. There's no Higgs. So it belongs in the trash can, yes, because it was an amazing idea. It was one of the best ideas of beyond the standard model. Sadly, that's not the way the world works. So, or not sadly, whatever, it's just not the right model. Okay, because there's no Higgs here. It had other problems already because it gave you large corrections to electroweak precision observables. But that one, you could always argue that maybe there's a way out. You don't know exactly what the strong dynamics is. Maybe not exactly like QCD. Maybe the correction is not as large, etc. But the fact that there is no Higgs, that's really a killer.
Do all the planets need to be absorbed by
No. No, yes, because they would be pions, so they wouldn't have. Well, first of all, so mimic a Higgs. Yes, the Higgs is giving you. Well, okay, so that's of course the thing that we are going to be talking about. Yes, that the strong dynamics is producing a Higgs and doesn't break the chiral symmetry. Yes, and then those Higgses, yes, will be composite. Yes, so from that point of view, yes. Now, if you are saying, could I have something where I have, a condensate and a Higgs? Yes, that's also possible. Yes, it sounds a little bit like overkill. Yes, But I mean, people are talking about this very seriously. Yes, so there are some there's something called bosonic technicolor. Yes, where most of the electroweak symmetry breaking is actually done by the Higgs, but it's the Higgs potential that is going to be triggered by this by this condensate. So there are versions of doing it. I think I will not talk about those. Those are getting to be a little bit complicated, but so there are all possibilities. Now, what is not possible is that you have this condensate plus the normal Higgs, yes, because then you will get too large a mass of the. I mean, the two together must give you the correct, and then you expect that one of the two will dominate. Yes, in fact, it should be the Higgs that is dominating. Yes, because then you are also okay with electroweak precision. So. No, the technique quark. Yes, will you are not supposed to see it because it's supposed to be a confining theory. This scale is supposed to be 1 TeV, yes, or something of that order. So they're supposed to be technihadrons, yes, but they are supposed to be heavy, yes. So well, now maybe because we know that there are not too many particles even at 1 TeV, yes. Now maybe even that is excluding technicolor, yes, but again, it depends on exactly what the spectrum is, how they're interacting, so that's not completely obvious. Okay. All right, so anyway, that was a great idea. It doesn't quite work, yes. So the next idea, the one that we will be spending our time on, is that the strong dynamics produces a composite Higgs. Okay, very good. So in this case, the solution of the hierarchy problem would be so here the solution of the hierarchy problem is, well, there is no Higgs. Yes, that would be the solution in technicolor. Yes, there's just no scalar. There's nothing to calculate the corrections to. Yes. Now, in this composite Higgs model, the solution of the hierarchy problem would be that there are scalars, but there is no elementary scalar. Yes, it looks like an elementary scalar below the scale of confinement. Yes, but once you reach 1 TeV or whatever that confinement scale is, yes, at that scale you are going to you are going to see that this Higgs is sort of dissolving. Yes, so basically there is a form factor in the Higgs, and this is just the bound state of fermions. Okay. So that's all good. However, so let's say that you have this lambda strong. Yes. So this lambda strong, whatever technicolor or whatever the strong interaction is, let's say it's 1 TeV. Yes. Now the problem is that you're expecting your hadrons to show up roughly at 1 TeV itself. Yes. So you would think that, well, okay, if that's what is happening here, yes, the Higgs itself should be showing up at 1 TeV. Okay, but of course we know that it's not. It should be still much lighter. So in order to make this a viable scenario, to bring the Higgs down from 1 TeV to 125 GeV, yes, you need an additional ingredient. Yes, so that additional ingredient is going to be the pseudo-Goldstone boson idea. Yes, so there are two things that go into these models. Yes, one is that there's a strong dynamics, the Higgs is composite, but on top of it being composite, yes, it should also be a Goldstone boson, such that it can be lower, yes, than the scale of strong interactions itself. Okay, so that's the full logic of these models. Okay, so let's try to write down a strongly coupled theory, yes, that produces the Higgs as a Goldstone boson. Okay. So how to write the Higgs as a Goldstone boson? Yes. And well, there are many things that this theory has to satisfy. Yes. So this has to have, well, I have to be able to embed the electroweak interactions into it. Yes. So somehow SU2 left has to be embedded. Yes. And the Higgs should be a doublet under this SU2 left. Yes, because that's what the Higgs mechanism does. Okay, so those are the lowest order requirements. Of course, there are other requirements that are hard to satisfy. Because it should be a doublet. It should be a Goldstone boson on one hand, so to be protected, but it really shouldn't be a Goldstone boson, yes, because we know a Goldstone boson doesn't have a quartic. Yes, the Higgs has a quartic. The Goldstone doesn't have a quartic. Yes, it should interact with the gauge fields. Yes, I mean all of it should have a it should have a mass term, yes. So it cannot be a true Goldstone. It has to be a pseudo Goldstone, yes. And you have to make it such that whatever makes it a pseudo Goldstone does not push up its mass to 1 TeV. Okay, so that's the task that we are trying to get to. Okay, so let's see. So the simplest way, yes, is so we have to start with some global symmetry, yes, that is broken to some smaller global symmetry, yes, and so this should contain SU2. Yes, well, the simplest thing that could possibly do this is to take an SU3 and break it down to SU2. Yes, so the simplest idea, take an SU3 and break it down to SU2. Yes, and eventually the SU2 you will think of as being actually the SU2 of the weak interactions. Okay, so if you have this kind of breaking, where will the Goldstone bosons be? Yes, so what I'm drawing here is the adjoint of the SU3. Yes, so that's a traceless Hermitian matrix. Yes, so that's the adjoint of SU3. Yes, and the Goldstone bosons will live in the directions that are being broken. Yes, by the vacuum expectation value of whatever is giving rise to the breaking. So if this is the full SU3, yes, and then this is the SU2, this is the unbroken part, yes, which are the directions that are going to be broken by going from SU3 down to SU2, yes, well, these directions will be broken, yes, and then of course, there will be one combination of these diagonal directions, basically the what is called the T8 direction, yes, that's the other direction that is being broken when SU3 is broken down to SU2. Yes, so there will be some, I'm going to write here these little dots, but it means that this is just one field, yes, this is in the combination 1, 1, minus 2. Okay, so yes, you expect 5 Goldstone bosons in this breaking, yes, because SU3 has 8 generators and SU2 has 3 generators, so 5 generators are broken. You expect 5 Goldstone bosons, and so you can write the pion matrix, yes, as your Higgs doublet, yes, your complex conjugate Higgs doublet, and then there's this additional field. Let me call this for now an eta, and I forgot what the normalization is, √6. It doesn't matter. The eta won't play a role, at least here. Minus 2 eta over √6. Okay, so this is the pion matrix. Yeah, so this is the matrix what we used to write as pi a ta, yes, for the QCD case. Yes. Now in this case, when SU3 is broken down to SU2, you will write it in this form. Yes. So there are these 4 generators. Those will correspond to 4 real degrees of freedom. You can, because this is a Hermitian matrix, yes, you can write it as a doublet here and the conjugate of that doublet, yes, plus this additional diagonal guy that we won't care about. Okay, very good. So that's very nice, because at least the lowest task we have accomplished. Yes, we found a Goldstone boson that is a doublet of an SU2. Yes, I mean that's already something non-trivial. Now, how should I then introduce the interaction with the Electroweak interactions? Yes, well, let's just do the obvious thing, yes, and say that I have an SU3 which is spontaneously broken to SU2, yes, and let me gauge this SU2 subgroup, yes, because okay, how, what will be the effect of this? Well, we know exactly what to do here, yes, we just turn the crank of what I told you, how to write down these chiral Lagrangians, how to put in gauge interactions, and we can go ahead and calculate the corrections to the mass of these pions. Okay, well, so the nonlinear sigma model field, I'm going to write it as phi, yes, it's just this e to the I pi a t, let me write it just pi over f, where this pi is this entire matrix over here. Okay, and this is going to have to act on a field that has the VAV of the form that is giving rise to the breaking SU3 down to SU2, yes? So if I take a triplet of SU3 and give a VAV to one component, that is going to give the breaking SU3 down to SU2. So this is my nonlinear sigma model field. So that's perfect. The pion matrix is what I have written over there. I can actually expand this if I want in terms of the Higgs field, yes? So let me expand this explicitly. So it's going to be IH, and then it's going to be F minus H dagger H over 2F. Okay, and I have set that eta, that annoying eta, to 0. You can add those contributions also as plus higher order terms in the Higgses. Okay, so this is the leading expansion of the nonlinear sigma model field in terms of the pions. Yes. So now gauge the SU2 subgroup. Yes. So my covariant derivative is going to be d mu minus IG times W mu A times this matrix where I just put the tau A over 2 into this 2 by 2 form. Yes. And I can go ahead and start calculating what my Lagrangian will look like. D mu phi dagger, d mu phi. Yes. So that will be the leading term in my effective Lagrangian. Okay. Oh, yeah, this I cannot write. What did I put that line there? And what do I find? Well, I'll start writing out this Lagrangian, and I will get here the d mu of the Higgs doublet, h squared, yes, plus I will get a correction, d mu h squared times h dagger h over f squared. And most importantly, this piece here, yes, is just the normal d mu minus IG W mu A tau A over 2 acting on the Higgs. Yes. Well, this doesn't look so good, yes? Because I look at these interactions with the W, yes, and I find that the Higgs mass is as quadratically divergent as it used to be in the standard model. Yes, it still gives you a g squared over 16 pi squared times lambda squared h dagger h. Okay, so that's not very good. Should we be surprised? Should we be surprised? Well, not really. Yes, basically we added the standard model interactions. Yes, and we didn't add any new particles into the theory, yes, except of that annoying eta. Yes. So what should cut off this? There's nothing to cut off this divergence. Yes. Another way to say it, we introduced the shift symmetry to protect the Higgs, yes, but then by gauging the SU2 subgroup, I broke that shift symmetry immediately, yes. So the explicit breaking, yes, that was there to give you the interaction between the Higgs and the W, which is absolutely necessary in order for the Higgs to give you the mass of the W and the Z, will give you the quadratic divergences back. Okay, so that's not good. All right.
But we're still in better shape because now lambda is the cutoff of like when a positive starts, right?
No. Let's say if you want, for example, lambda to be of the order of 10 TeV, yes, then this will give you still a correction. And why would I want lambda to be 10 TeV? Yes, because, for example, of electroweak precision constraints, yes, then this will give me a correction of the order of, so this is the little hierarchy problem, yes. Of course, in this theory, there is no fundamental scalar. So by definition, I sort of solved the big hierarchy problem because I just say so, yes. But there's still this problem, yes. Okay, very good. So slightly, yes. Oh, right. So we'll get to that, yes. So first, I won't do that today, but at least I want to show you what is the very basic model, the simplest one, where you can fix the gauge interactions, and then of course I will show you exactly also what to do with the Yukawas. Yes. Right. You can play with that. I have written papers on it, but yes.
If I just apply the same logic, the pion will get a mass at the cutoff scale.
Well, sorry, which pion? So the H is the pion, yes?
Yes, I mean, just now, going back to QCD, I have the same situation just like this. Then would my pion get a mass?
Well, one loop suppressed, yes. One loop suppressed. And it does, yes. I mean, the pion is not 1 GeV, yes, but it's a, it's 100 MeV, yes. So
would it get smaller than 100?
It's
I see.
yes.
Smaller.
Yes. All right. So let me just, because I really want to get to the point that shows you at least what the right model is. Okay. So I just want to show you one other trick. Yes. How to see this quadratic divergence showing up in a more fancy way. Yes. So what I can do is I can write this interaction term between the W and my nonlinear sigma model field in a slightly fancier way, yes. I will write it like this, W mu 0, where this is a 3 by 3 matrix, times phi, absolute value squared, yes. And so what this is telling you is, yes, that the mass of the W, yes, depends on the nonlinear sigma model field. Yes. So the mass of the W is depending on this combination, yes, where this is just a fixed matrix, yes, this matrix is 1, 1, 0, yes, basically the third component is projected out, yes, times this nonlinear sigma model field. And then I sort of see directly from the Coleman-Weinberg potential. So the Coleman-Weinberg potential is the one loop effective potential for scalars. And basically it's just saying the way you have to do this is you calculate the masses of all your particles in the background of these fields turned on. Yes. And the leading term is just the quadratic divergence, yes, times the trace of the mass matrix of whatever particle is showing up in the theory. There is, for fermions there's a minus sign, for bosons there's a plus sign, and there's a number of helicities. But the important thing is, yes, that what shows up here is m dagger m. Yes, so this will be this this term that is phi dagger m dagger phi times trace of that. Yes, and this is actually, when you look at my expression for what the phi field is to leading order, yes, it is sadly just going to be H dagger H. All right, so that's why you get this quadratic divergence. Now what you see is that if you didn't have this projection, so if this was a unit matrix, yes, then I would be in much better shape. Yes, because then I would get there phi dagger phi, yes, and phi is exponential times the pion, yes, and so the pion would drop out, so I would not get a quadratic divergence. Okay, so a better way to do this, or at least so it looks like, is to say, well, let me gauge the entire SU3. Yes. So in that case, yes, you will have more gauge bosons, yes, and your Coleman-Weinberg potential will look like g squared over 16 pi squared lambda squared times phi dagger times this unit matrix times phi, which is now pi independent. So is this victory? Almost, but not really, because, okay, so now what did I do? Yes, I gauged the entire SU3 symmetry.
Breaking.
Uh,
The whole SUC, how can you break any?
No, I mean there's still, there's still a web. Yes, the important thing is the gauging now is not an explicit breaking. Yes, so the goldstone remains a true goldstone, but it gets eaten. Yes, so there is no goldstone. Yes, so no quadratically divergent mass. But also no pi. That's too bad. Yes, still not good. All right. Well, the final version, and I will just write down this final version and then explain why this works, I guess, tomorrow. Final version is to say, well, what I can do is I can sort of be tricky and introduce two of these nonlinear sigma model fields. I have a phi 1 and a phi 2. Yes, and each of these will have its own goldstone. So that means that instead of looking at SU3 broken to SU2, I will look at two copies of SU3 broken to SU2. So that means that I will have an SU3 broken to SU2 version 1 that is described by this nonlinear sigma model field, and I will have another version, let me call this 1 and 2. Each of these will have their own pions. But I'm only going to gauge the diagonal subgroup of the two SU3s. Okay, so that's an explicit breaking of the entire SU3 cross SU3 global symmetry, but one SU3 symmetry is left unbroken. When I do this explicit breaking, yes, then both of these SU3 broken to SU2 is going to give you a mass to the same set of W's. Yes, so one set of these goldstones is going to be eaten, but one set is going to remain physical. So one set eaten, but one set remains. Yes. And now if you write down what your Coleman-Weinberg potential is, yes, your Coleman-Weinberg potential will look like lambda squared over 16 pi squared g squared times phi 1 dagger phi 1 plus phi 2 dagger phi 2. Okay. So now this is victory, yes? Because there will be one set of goldstones living both in phi 1 and in phi 2. Yes? But from this formula, they will drop out. Okay? So there will be no one-loop quadratic divergence to the goldstone bosons. They will be there. They will be doublets of SU2. Yes? So this is the kind of thing that we want. All right. I'll stop here. this just that you know, this is what is called the simplest little Higgs model, because it's a model of Martin-Schmalz. And the reason why this actually works is called collective symmetry breaking. Okay, so we'll continue with that, explaining what collective symmetry breaking is, and how to include Yukawa couplings, etc. tomorrow. All right, thank you. Questions?
Explain what G star is.
So G star is the interaction strength among the composites, among the heavy guys. Yes.
So is it like a 4 point?
So G star could be, so it should be less or equal than 4 pi. It could be at most 4 pi, like any coupling. Yes.